Okay, we've been talking about light, and we're going to continue talking about light. Today, we're going to talk about how lenses and mirrors can form images. So we saw from last class period how a mirror, if it has the right, or a lens, excuse me, if it has the right shape, it can bring light together. And if it has a different shape, it can separate the light. And we talked about the focus and what that means. Now, as we start talking about making images, we do it both graphically and using an equation. For the next exam, you are going to have to do a graphical solution that you're going to have to draw rays to show where the image is formed. Hannah, can you move the water? Remember, we are now using harmful chemicals in here, so we want to have no food or drink out.
Where do I put it?
Wherever, it won't be on the table.
Okay.
So when we're making our diagrams for, on the test, for instance, some things we need to know are what terms like the principal axis means, the optical center of a lens. So we start with basic things. Here's a lens. This lens has two surfaces that are convex. Hence, we give it this really amazingly obscure name of biconvex. Where's its optical center? Well, if we draw the principal axis goes right through the center and perpendicular to the axis connecting the edges. So, whoops, get that out of there. This here is what we call the principal axis. And I can't remember, yes, it's our buddy, the principal. Not a principle that we follow in our daily lives. And the optical center is that point right there, where the principal axis goes through the center of the lens. Now, these are important things because as we draw ray diagrams, we're going to use those. So I'm not going to jump right into a ray diagram. I'm going to remind us we have a diverging lens. What would you call the shape of this lens? The one I just wrote by below. Biconcave, because it's concave on both sides. It diverges the light, so the light doesn't come to a focus, but we still identify a focal point. How do I identify a focal point if it doesn't come to a focus? You extrapolate backward. And so this here, okay, my picture, my hand drawing did not match where they had drawn the capital F. Remember I said in class on Wednesday, we use a capital F to indicate the focal point, the point where parallel rays meet. In this case, it wasn't the parallel rays that met. I'm going to erase all of my stuff because it didn't meet there. And you all understand that that was my artistry that was failing. I suppose I could have used the line tool here. And you would see that, yes, they did it right, which is a good thing. So we have the focal point F is where parallel rays meet. And then we talk about the focal distance being the distance from the center point. What do we call the center point? Optical center. The distance from the optical center to the focal point. That's the focal length. And we use a lowercase f for the focal length. So that was for the diverging lens. For the converging lens, we likewise have a focal length coming out here to where the rays met. There it's a lot easier. You can see them meet. Which one of those two focal lengths is positive? The converging one is positive. Two ways of analyzing our numbers. One is if it's a lens and it's on the opposite side of the incident light, then it's positive. The other is if it goes to where the light should go. So if it's a lens, light should go through. So if it's on the side that it went through to, it's positive. If it's on the side that the light started, for a lens, it's negative. For a mirror, it's reversed because the light should reflect back off a mirror. So we have that focal length, and with that, we're actually ready to start figuring out where an image is going to occur. Now, we need to pay attention. Everything we're doing in this class is for thin lenses. Why a thin lens? I took out about 7 slides going on and on about thin lenses. But in the reality of a lens, it doesn't change direction at the center. Where does the light change direction? At each surface. So if I was accurate with this drawing, and like I said, I took out a bunch of inaccurate pictures, or excuse me, I took out a bunch of accurate pictures. If we were accurate with this, the light would be doing something like that. And it would be shifting in height from the front surface where it went in to the rear surface where it came out. And that shifting in height actually makes a difference if you have a thick lens. If you have a thin lens, that shifting in height is not significant enough to make a significant difference. And so our thin lens approximation is to say that the light just makes one change in direction instead of 2, right? Instead of changing at each surface, just one change at the center. That's our thin lens approximation. And if we truly had a thin lens, if that was truly correct, then we would have perfect solutions. So what we're doing is finding an approximation, but a key here is that the lenses we're going to use are relatively thin compared to their sizes. So our lenses are, the thin lens approximation works for it. You might have seen, I have a lens somewhere that's about this big in diameter and about that thick. That's not going to work for a thin lens equation, right? So you have to pay attention to that. For this class, everything we'll treat as a thin lens. Also, we restrict ourselves to these, let's underline it. What do you say? Paraxial rays. Paraxial means parallel to the principal axis. Not perfectly parallel, but pretty close to parallel. So all of our rays are going to be pretty close to the principal axis and parallel to it or close to that. We're not taking angles that are crazy. Even though in our pictures they'll look like crazy angles, in reality they're not. Because, I told you spherical shape isn't the proper shape. And so if you go way off the axis, that non-correctness of the spherical shape has a bigger effect. So we've looked at pretty much all of this. I'm skipping through. Here's the actual naming conventions. I said biconvex and biconcave. This is double convex and double concave. I'm pretty sure you're flexible enough to know that bi means double. So you see both terms. Plano, that means one side is planar. So this is plano-concave, plano-convex. Now, if I look at this lens right here, you can see from above it says diverging, but one side's flat. How is it diverging if one side is flat?
Where the light is shining from?
Well, it'll be diverging regardless of where the light is coming from. And I can show you that. Put the screen up, turn the lights off. So, turn the lights off, and yet I have the projector on still. Yeah, this is for lab next time we have lab. So here is a planar side facing here, comes out diverging. What's happening at the first surface here? Nothing. It's just going straight through because it's coming in normal to the surface, hence no change in direction. But it's coming out and you have different angles for where it's coming out. The lower you are, the normal is pointing more toward the center, and so it bends away because it's going in faster medium. Higher, again toward the center, so it bends away from center. Turn around. Now what's it doing in the front surface? It's changing direction. It's now bending toward the normal, which is going away from the center when it goes in the first surfaces. The second surface, what's it doing? It's bending away from normal again. Because it's not normal, it's bending away. So here it's actually bending on both surfaces. You actually have a better focus in this case because it's bending the same on both sides. This direction here, while it has the same focal length, it's not as good of a focus. It's not as reproducible. And the same is true if I reverse it. Here's a plano convex. You see it's coming to a focus, and you can see the focus is not perfect. You have some crossing back here, some out here. Flip it around like this, and you see that focus is a much better focus because it's doing equal bending on both surfaces. So if you ever go into designing optical systems, that's something to keep in mind. Okay, moving on from that, we have one more pair of lenses that needs an explanation. Somewhere in this process, I set down my stylus. There it is. This here, the meniscus means that both surfaces are curved in the same direction. So one is convex, one is concave, so that they're both curving the same way. Their center of curvature is in the same direction. Center of curvature is if you draw a circle, where's the center of that circle? We have a concave meniscus, the one I circled there in red, and then you see a convex meniscus that I'll circle here in green. They're both meniscus. That is, they both have the center of curvature is on the right side for both of them. One of them's diverging, one of them's converging. What's the quick and easy way to tell? Okay, the top is thicker than the middle here. That makes it diverging. The top is thinner than the middle here. That makes it converging. So we have a few people here wearing eyeglasses. If you feel the thickness of your lenses in your eyeglasses, are they thicker in the center or on the edge? Thicker on the edge. So which type of lens is it? Okay, if it's thicker on the edge, it's diverging, and it's the meniscus type. Our eyeglasses are the meniscus type where the center of curvature for both of them is toward the eye. Both lenses are curved toward the eye. Why do they do that? Once again, to try to have equal amounts of bending on the front surface and the rear surface so that you have a better focus. So you can always just feel your eyeglasses to see which one it is. And we'll talk about vision correction probably on Monday following break. Okay, now let's get into ray tracing, how we form an image here. How we form an image from a lens using geometry. So I'm going to start by drawing my principal axis, and then I'm going to put my lens on it. So I'll put a lens like this. Based on its shape, is that a converging or a diverging lens? Okay, it's a converging lens. Now I need to identify the focal point. So this is where things break down because I'm not using a ruler. On your test, you'll need to use a ruler. It'll have to be an accurate diagram. So I'm going to, I'll use one of my business cards to try to measure and say there's the focal point on one side. There's the focal point on the other. So I marked both focal points. I'll put an F here to tell me where each one is. And then I'm going to place an object. For physics problems, we draw the object always as an arrow that goes from the principal axis normal or perpendicular to that axis. So there's my object to, once again, the best of my abilities. So now the question is this object going to form an image? And if it does form an image, will it be a real image, one where the rays actually meet, or a virtual image, one where the extrapolations of the rays meet, but they didn't actually meet? Will it be an upright image, where it's pointing the same direction as my initial one, or will it be inverted, pointing the opposite direction? The reason we put the bottom of the arrow on the principal axis is because we only have to analyze the top of the arrow. because the image of the bottom of the arrow is going to be on the principal axis as well, and so I don't worry about that one. So that's why we show the arrow going from the principal axis up. So I need to draw some rays, and I'm coming up here just to make sure I choose my colors. So I use green for parallel. Yeah. So first, the parallel ray. What direction is light coming from the tip of my object? What direction should light be leaving is what I meant to say. Okay, all directions is the answer. So I'm going to focus on the one that is parallel for my first ray. So parallel means parallel to the principal axis. This is better with other drawing programs where I can, well, there is a way to make a straight line. It's just a hassle. Let's see if I can do that quickly. Nope, not that. I don't even remember where the tools are. I thought it said tools here before. Not there. Insert, signature image, measure, shapes, text, shapes, line. Green line. Okay. Green line. There's my parallel ray. Where did I go to with the parallel ray? To the center of the lens. In fact, I usually actually mark the center of my lens, and that's where I'm going to make all my rays go to and end. Where does a parallel ray go when it goes through a converging lens? By definition, it goes through the focal point. Parallel rays all go through the focal point. So that's why I started with the parallel ray. So by definition, it goes like that. Now I'm going to name this, that's the parallel ray, or the P ray, the prey, if you will. Light is leaving the tip of my object and going like that. So there's my first ray. Now to get my colors right, the focal ray is the one that I have in blue. So now we go to a blue line. Focal ray. The focal ray is a ray that goes from the tip of my object through the focal point on the same side, if it's a converging lens. So it's going to start here at the tip and go through the focal point. Now you'll notice that my line goes down below where I had drawn my lens. That's okay. This is just a construction. Now in real life, that wouldn't contribute, but the image would still be the same place. So I'd still use the same construction in real life, even if that ray itself doesn't contribute. Well, if a ray that's parallel goes through the focal point, where is a ray that goes through the focal point going to come out? Parallel. Light works the same way forward and backward. So that ray is going to have to come out parallel. Uh-oh. It looks like the scale of my picture is not going to work. But we'll move on. Because do those two meet? Yes, but not on my screen. And no, I don't have more space. So that's the focal ray. So we call it the F ray for focal ray. That was light again coming from the tip, going through the focal point, and then coming out parallel. The last one is called the vertex ray. I'm going to do that in red. And so the last one goes through the vertex and goes through unchanged. If you have a no thickness lens, at the center point, what are you going to have for the relationship between the sides? At the very center. They're going to be parallel. So because they're parallel, it'll be just like when we did the light going through the pane of glass, not plane of gas. The pane of glass at the beginning of last class period. It was offset a little, but came out parallel. If it's a thin lens, one of negligible thickness, then there's no offset and it just goes straight through. And so this one here is called the vertex ray or V ray. And where the three meet is where the image is formed. Now, I could have done this with only 2 rays, but I am going to require 3 rays. Why suppose I require 3 and not just 2? Yeah, because 2 of them are always going to meet. You do the third one to make sure that you actually did it correctly. If the third one meets with the other 2, then you know you did it correctly. So that's why I always require 3, not just 2. So a question on this, actually, I'm going to keep this on that tool because I'm going to use it again later. Which ray does not apply to a lens? So which one did I not use in that picture? Caitlin and Mahala. I want people to get their points. See if she makes a tie or makes a winner. Okay, so we had 1, 8. It worked real nicely for the 1 though. 8, 0, 7. Not very good because we only used 3 rays and I named each one of them. What was the first one I used named? The parallel ray. So it can't be this one because that was the first one I used. Parallel ray, when it goes through the lens, how does it come out? Goes through the focal point. What was the second ray I did? The focal ray. So it couldn't be that one. When it went through the focal point, how did it come out? Parallel. The third one, we're obviously almost 50-50 split. Which one was the third one? It was the vertex ray. Whoops, can't put a circle around because that's one of the ones we used. So all the ones with X through them we used. What does that leave? The center ray. The center ray is going through the center of curvature. Right, we haven't talked about it, but when you do a mirror, you can use the center ray. A center ray will go and hit the mirror at a right angle. That is normal to the surface. If it hits normal to the surface, where does the center ray reflect back off of a mirror? Straight back where it came. But with a lens, you don't have that option. So that's why the center ray is only for a mirror. Okay, so we've done a ray construction. Here's what it would have looked like if I'd given myself room. We have the parallel ray goes through the focal point on the opposite side. The center ray goes right through the center. The focal ray goes through the focal ray on the same side. Now, I have to add one little caveat to that. The focal ray goes through the focal point on the same side if you have a positive focal length. If you have a negative focal length, it's going to go to the one on the opposite side. So, to be a little more accurate, the focal ray goes through the focal point associated with the side you're starting. But if it's a diverging lens, the focal point associated with the side you're starting is on the opposite side. So there's a variation there. So you have to pay attention to which focal point you're using. If it is a diverging lens, you go to the opposite one. Now, here's a ray construction for a diverging lens. A lot quicker to have them pre-made. It has the same 3 rays. What do we call the green ray here? Parallel ray. Where's the parallel ray supposed to come out? I said it goes through the focal point. Well, because this is the diverging lens, the focal point associated with the exit side is actually on the entrance side. It can't come back to that point. And so instead we extrapolate from that focal point, and then we have the direction the ray is going, because it's as if it came from that focal point. Let's go to the blue ray. The blue ray is headed toward the focal point on the far side. To make this clear to me, by the way, you know what I always do? I didn't do it in my picture, and I should have. I always actually mark these as F and F prime. F is the focal point associated with the object side. F prime is the focal point associated with the, or excuse me, I said that backward, genius. Okay, so F is associated with the object side, F prime with the image side. And so here I would have had F and F prime. And here it would be reversed. The object side has its focal point associated with it over there, or yeah, the image side over here. So goes toward there. You can see the extrapolated line here is going through that focal point, and then it comes out parallel. Oops. How did I get an F prime on both sides? Should have just had one. So this comes out parallel. These two rays are never going to meet, right? Never, ever. I finally draw the third one, the vertex ray that goes straight through. The place where those three rays extrapolate to meeting, that's where the image is formed. And so the image is drawn in there. Is that image real or virtual? Virtual. What was the hard rule that tells you it's virtual? I didn't hear what you said. You stopped halfway through. What did you say, Katie?
If the light coming directly from the object?
No.
If the rays actually meet, then it's real.
Okay, if the rays actually meet, then it's real. Now, the reason I said no there, Katie, is because now light gets to there from just one point on the object. The other two rays, you don't have it directly getting to the image position. Right? Only the vertex ray actually has light getting to that point. But on the output side, if we just take the extrapolation, your eyeball says it looks like all the light actually met back there. It didn't really, hence the term virtual. It looks like it, but it didn't. Whereas if the light actually met, then it would have been real. Now it says virtual image. Is it upright or inverted? Upright because it's pointing the same direction as our object. So this is upright and virtual. Finally, is that magnified or diminished? It's diminished because it's smaller. Now let's go back to this picture. Is that real or virtual? I know it says. It's real. Is it upright or inverted? Inverted. Is it magnified or diminished? Diminished. Now here's some simple rules just in case you make a mistake somewhere. If you have a single lens or a single mirror, these two always come as a pair. If it's real, it's going to be inverted. And whoops. These three always come as a group. If it's upright, it's going to be virtual and diminished. Actually, is that right? No, that's only true if you have the right kind of lens. So I'm going to temper that and just go these two. Because if you have a different type of lens, you can make it enlarged, the virtual. So upright and virtual always come together. Real and inverted always come together. The diminished or magnified will have to do with the object position as well as the type of lens. So object positions. In this case here, I had the object farther away than the focal point. How would it have changed if I had the object closer than the focal point? Okay, be magnified. Let's just quickly do the ray diagram. So starting off with my principal axis, drawing a vertical line for the center of my lens. Actually, get rid of that. I can put the center of the lens over here to give me more. Nope, change my mind. Back to where I started. Put the focal point. And so this is going to be like that. And now I'm going to put my object between the focal point and the lens. This lens is not drawn in, but I'll make it again another perfectly drawn biconvex lens. Let's go for the rays. What's the first ray I should draw? Parallel ray, which I believe I used green for, right? Am I right? So parallel ray comes in parallel, and how's it going to bend? Toward the focal point. Okay, next ray. The next one was the focal ray. Well, I'm inside of the focal point, so how do I do that one? Well, the rule was if it comes from the focal point, it comes out parallel. So I take a line that starts at the focal point, goes through my tip, and then hits my lens. This part, I actually can't erase part of it to make it dash, but the part between F prime and the tip is not really there. It's just to give me the direction. That's going to come out. If it goes from the focal point, how does it come out? Parallel.
Why do you have your F prime on the left side?
Hopefully I did that right, because the focal point associated with the incident light is on the far side. The focal point associated with the exit light is on the near side. Right, that's parallel rays on the incident side go through F. Parallel rays on the exit side came from F prime. Hopefully I was consistent in that.
It seems like you didn't do that for the first one.
Let's go back and check, because being consistent is, an important thing. And yes, this one here is inconsistent. Crap.
So F prime should go.
There, now it's consistent. Yeah, that's my way of remembering.
Is it opposite for concave,
And
or is it still?
the F and F prime should be opposite for concave versus convex. And here I also was, I was consistently backward of what I was very consistently backward. Now I'm hating myself. Don't hate yourself. It's bad. Okay, so I'm glad you pointed that out, just so we can confront what happens when teachers make mistakes. They get embarrassed. Moving on to the third ray. What was the third ray? The vertex ray. So my vertex ray goes from here and keeps going. Are those rays ever going to meet? Easy answer, no. Does that mean no image forms? No. If they're parallel, then we say an image forms at infinity. If they're not parallel, then we say, well, wherever they extrapolate to meeting, that's where the image forms. So I'm now going to reverse these lines, doing my best at reversing the lines. Oops. I swear I hit it. I guess I should have noticed that it was still on red and didn't change to green. Do they all meet perfectly? It's not perfect. You know why? I'm not perfect, which we've already seen. We can also see that I drew that the wrong place. That's close enough for me. So there's my image. When you're drawing this, you've got to do the best you can. Is that a virtual or a real image? Virtual. How do we know it's virtual? They don't actually meet there. Those were extrapolations. Is it upright or inverted? Clear answer. Upright. Is it diminished or magnified? I'm going with magnified on this one. So this is a magnified virtual upright image. I know I'm putting them in opposite order. So if we have the object closer than a focal length for a converging lens, it makes it a virtual image. If it's farther, it made it real. There is another separator. If you go farther than 2 focal lengths away, it will be magnified. If you go closer than the other way around. If you go farther than 2 focal lengths, it will be diminished in size. If you go closer than 2 focal lengths, it will be magnified. So the position of the object with respect to the lens will make a difference. And you can go through all of those. The last thing to show here is the geometry so that we can do this with equations instead of having to do lens drawings every problem we get, array drawings. So here is a simplified geometry. It's only showing 2 rays, the parallel ray and the vertex ray. And so with these rays, we're going to have this angle here has to be the same as this angle because it's the angle we've seen between the same 2 lines. And so we can make the relationship that tangent of that angle is opposite side, the height of my object, divided by the distance of my object. You see here I use d sub o for object distance. On the other side, it's the height of my image divided by distance image. Why is there a minus sign there? Because it's inverted, that's right. So this is one relationship that's going to relate the height and the image and object distance. Now I can take this and solve for the magnification. Magnification is defined as the height of my image divided by the height of the object. If the height of the image is bigger than the object, then it's bigger than 1, right? But from that relationship, that's equal to minus the distance image over the distance object. We use a lowercase m for magnification. And so there's a fundamental relation for the images we're producing. The magnification is defined as the height of the image over the height of the object. But it turns out that based on geometry, it's also equal to minus the image distance over the distance object. So if the distance image is positive and the object distance is positive, you're going to have a minus in the magnification. What does that minus sign mean? It means that it's inverted. So the minus sign tells us if it's inverted or not. If the magnitude is bigger than 1, it's enlarged. If the magnitude is less than 1, it is diminished. So there's one relationship. Now the other relationship, of course I had that. The other relationship comes from looking at the angle again, but now, or not that angle, a different angle, looking at this angle here and this angle here, which are labeled as beta. This here is 1 focal length away, and this is the height of the object. So tangent of beta is height of the object over the focal length. Going to the other side, the distance that I just drew is the image distance minus the focal length. We actually have a name for that. It's called the extra focal length. And then we have minus h prime, minus because it's inverted, h prime for the image height. And so this gives us a second relationship. But from the first mathematical relationship, we had that h prime is equal to minus h distance image over distance object. right? From the previous page, we had h prime over h equals minus di over do. So solving that for h prime, we have a simple relationship that I can plug in here. And if I do that, I'll have now, of course, minus and minus is plus. And notice I have h on both sides. So this simplifies to this. Now, if you look at that, you're like, well, shoot, that doesn't look all that useful to me. Well, we like to do a little manipulation to get the f's together, and I'm not going to show that manipulation. But it turns out that 1 over the focal length is 1 over the distance image plus 1 over the distance object. I don't think I made any mistakes. I just don't feel like going through the math to have to do all the work there. Yeah. So let's go to the second clicker question, or third, or whatever it is. A 3 centimeter tall object is placed 19 centimeters from a 25 centimeter focal length. Is this going to have a real or inverted image? And where is it located and how tall is it? Okay, so this isn't a clicker question. My bad. I haven't put in here as a clicker question, but these are actually separate questions. So let's answer these. A 3 centimeter tall object is placed 19 centimeters from a 25 centimeter focal length lens. Drawing a rough picture. Here's my lens. Here's my principal axis. Here are the focal points. It's placed here. Is that going to produce a real or virtual image? Virtual. Why do you answer virtual? Inside the focal length, so it's virtual. Is the image going to be upright or inverted? Upright, because if it's virtual, it's going to be upright. Where is it going to be located in rough terms? Not the actual distance, but in rough terms. It's going to be somewhere out here for the image. And how tall is it? Well, we would have to do the math for that. Taller, yes. Okay, so that was without the math. I'm not going to this website just because, well, we only have 5 minutes left. But this website here, what it does is it allows you to actually play around with problems. Like say you have a problem and it gives you a focal length and it gives you an object position. You can just take this and first, of course, clear everything and then say, well, I'm going to use an object because my problem had an object. And I'm going to use a lens because it had a lens. And then you can drag the lens wherever you want it. You can drag the focal point here to change the focal length. If you bring it across the lens, it'll change it to a negative focal length. So you can adjust the focal length. It tells you what the focal length is right there. And you can adjust the position of the object, see where the image is. It'll give you your answers. And it does it visually, showing you the ray construction. Now, this is shown with a mirror. That's another option. You can put multiple lenses. You can do all kinds of cool things. It's very cool because it shows you what's going to happen with the light rays. But we need to get to mirrors. Out of the way. Close enough. How are mirrors different? Let's play with mirrors. I have 2 kinds of mirrors here. So, what the heck? Let's start with this one. Concave or convex? Convex. So let's take Megan as our guinea pig. Do you see yourself in this, Megan? When you see yourself, what do you see for the image?
Upright.
Upright and diminished. Now I'm going to come toward you. What's happening to the image?
Getting bigger.
Getting bigger. Is it still upright? Okay.
Getting bigger, still upright.
Okay, bigger, still upright. all the way up against your face almost. It is?
Bigger.
Bigger and?
Upright.
Okay. So this always made an image that was bigger and upright. A diverging lens will do the same thing. That is, it'll always be the same. Now, you see yourself in this one. What do you see yourself as?
Inverted and small.
Inverted and small. So I come in, what's happening?
Getting larger, still inverted.
Okay, larger, but it's still inverted.
Larger, still inverted.
Still see yourself?
No.
What do you see?
It's me, really large and upright.
Really large and upright. So let's go back a little bit. There is a place where I say what you see is a meat pie. There's a place where there is an image behind your head. You can't see behind your head, it turns out. And so it's just out of focus and you just see a bunch of light. If I get closer then, it's which way?
Upright.
Upright and?
Really large.
And really large. So this fundamentally changed. If it's upright, was that a real or virtual image? It was virtual. If it was inverted, which one was it? Real. So this can make both a real or a virtual image. As you heard her describing, it can be enlarged or diminished. So how does this work? Just the same as what we've been doing. You have a focal point, focal length. I'm sorry, I totally am blocking. There. You have a focal point. You only need to put one focal point for a lens, or excuse me, for a mirror, because the light's gonna, well, I won't say that. Let's just do some ray diodes. If I have parallel rays coming into a mirror, they should all meet the same place. We're going to again use paraxial rays, so they're going to be parallel rays that are parallel to the principal axis. The focal point is where those parallel rays meet. So to do a ray drawing, I will, now I need to put in my mirror. Here's how I put my mirror in. Pay close attention. That's my mirror. It's straight. Why is it straight? Because I'm taking the paraxial approximation, which means I'm really close to that principal axis, and thus it's not going to have much appreciable curvature change if I'm close. I usually put something like this to tell me, hey, that's a concave mirror, by putting those little ticks at the top and bottom. That way I have where my mirror is, put my focal point. So here's my focal point. Now I'm going to put an object out here. Here's my object. And let's draw some rays. What's the first ray we did with a lens? Parallel ray. So let's do the parallel ray. Parallel ray. Where does the parallel ray go? Do the focal point. Okay, second ray, the focal ray, starts at the tip of my object, and where does it go? Through the focal point. And how does it reflect back? And what's my third ray? Okay, vertex ray goes to the vertex and comes back symmetrically. So what I do is I try to actually just measure this height and put the same spot down there to shoot for it. There is a fourth one, the center ray. If I had measured my focal length, the focal point, it turns out, okay, well, you can kind of see that. The focal point, it turns out, or the focal length, is 1/2 of the radius of curvature. So the center is just 2 times the focal length away. So finding the focal length for a mirror is just finding the curvature. And the center ray will go from the tip. Oh, Richard. Lord have mercy. From the tip through the center and then reflect straight back. So if I had measured that center correctly, I tried to do my best. Clearly I was wrong. That center one would have hit the same place the others do. So you have 4 rays for the mirror. If I give you a mirror for the test, you only need to show 3 of them. So you can choose which 3 you want. By default, I choose the parallel focal and vertex because those work for mirrors or lenses. But if you want the center, go for it for a mirror. Okay, we're out of time. Have a great vacation. I'll see you all on Monday. And on Monday, we really will start in with chapter 26.